Welcome to this HP Expert One presentation. This is the second video discussing IP routing. In the first video we looked at the basics of IP routing. In this video we're going to continue the discussion by looking at how distance vector routing protocols try to combat loops by using mechanisms such as split horizon, poison reverse, and others. Let's get started. So now let's look at distance vector routing protocols in more detail. Distance vector routing protocols advertise their entire routing table every few seconds. So as an example, RIP will advertise the entire routing table every 30 seconds, even though there are no changes. Not very efficient, but that's what they do. Each router tells its neighbors what it knows. Remember, this is like a road sign or routing by rumor. The routers do not have a full view of the topology like link state routing protocols do. I'm going to show you in the next few minutes some of the issues you'll encounter with regards to distance vector routing protocols, and then I'd like to show you the mechanisms or solutions to those problems. A very important concept to understand is that the clocks of the routers are not synchronized. So let's say on a timeline, at time 0, you enable RIP on router 1. 30 seconds from time 0, router 1 will advertise its entire routing table, and thereafter every 30 seconds. If you enabled RIP on router 2 at time 15 seconds, that means that there's a 15-second differential between the two routers. So on router 1, time 0, you enabled RIP. On router 2, at time 15 seconds, you enabled RIP. 15-second difference between the updates on these two routers. So the updates will occur at 30 seconds, 45 seconds, 60 seconds, 75 seconds, and so forth and so on. Notice there's a difference in the time between the updates between these two routers. It's important because this can cause issues. The times are not synchronized, so it's possible that the updates from one router override the updates of another router. Now, what I'm going to show you in the next few minutes are issues caused by the fact that the clocks are not synchronized. The developers of the RIP routing protocol have implemented mechanisms to try and combat routing loops and other issues. So let's look at the issue first, and then we'll look at the mechanisms to stop routing loops. So let's start with a simple topology. Router 1 has network 10110 directly connected to FOST Ethernet 00, so that's been added to the routing table. 10121 is directly connected to FOST Ethernet 01, so network 10120 has been added to the routing table. Router 2 has something similar, 10120 directly connected to FOST Ethernet 00. FOST Ethernet 01 has network 10130. FOST Ethernet 0 on router 3, 10130. FOST Ethernet 01, 10140. So at the moment, the routers only know about directly connected interfaces. RIP hasn't been enabled, but once RIP is enabled, hopefully the routers will learn about all of the routes in the topology. So now let's say RIP is enabled on router 1. Router 1 will then advertise network 10110 to router 2. Router 2 will learn about the network and add it to its routing table. Router 2 will assume that the same mask is used, so /24 is the mask associated with the route because the interface has a mask of /24. The next hop address will be 10121 and the local outgoing interface will be FOST Ethernet 00. Router 2 would then advertise that information to router 3. So router 3 will add a RIP route to its routing table with a cost of 2. The next hop is 10131 to get to the destination network 10110. Outgoing local interface is FOST Ethernet 00 and the hop count is 2. Now over time, the routers will update one another with routes. that are directly connected to them and that they've learnt from their neighbors, and eventually the routing tables will be fully populated. The network is said to have converged because all routers know about all routes in the topology. As an example, router 1 knows about network 10.140, this network on the right hand side. Router 3 knows about network 10.110, this network on the left hand side. Every router knows about every network in the topology. The network is stable, it is converged. Now, because of the way distance vector routing protocols operate, they are susceptible to routing loops. The analogy is they have a road sign to the destination rather than a topology map or road map. So the possibility of routing loops are more likely. So the developers of distance vector routing protocols have enhanced the routing protocols to try and stop loops. And some of the mechanisms that we're going to look at in the next few minutes to stop loops include counting to infinity, split horizon, route poisoning, poison reverse, hold down timers, and triggered updates. We'll look at each of these in more detail, but before showing you how these stop routing loops, let's look at our simple topology and see how routing loops are introduced when these mechanisms are not used. In most cases, you don't have to implement or configure the mechanisms listed here because they're built into the routing protocol. As soon as you enable RIP, these features are immediately enabled as part of the routing process. The developers and designers of the distance vector routing protocols have built these mechanisms into the routing protocol to stop loops. However, you as an engineer need to be aware that they exist, because in certain cases you might want to disable one of these mechanisms. As an example, you might want to disable split horizon in certain topologies. So let's look at a network, a possible problem, then look at how these mechanisms solve the issues. So let's start with counting to infinity. The network in this topology has converged. All routers know about all networks in the topology. Now it's important once again to realize that the clocks of the routers are not synchronized with regards to routing updates. So as an example, if RIP is enabled on router 3 at time 0 seconds, and then RIP is enabled on router 2 at time 15 seconds, there's a 15-second difference between updates. So at time 30 seconds, an update will be sent from router 3 to router 2, but only at time 45 seconds is the update sent from router 2 to router 3. Updates in RIP are sent every 30 seconds, but notice there is a difference between these two routers of 15 seconds. So restarting our timer, RIP has been enabled on all the routers, the network has converged. Let's say at time 0, an update is sent from router 3 to router 2. So that's at 0 seconds. 30 seconds from now, router 3 will send another update to router 2. 15 seconds from now, router 2 will send an update to router 3. However, let's say at time 5 seconds, this link goes down. So there's a problem with a cable or some other issue. Router 3 will only send an update to router 2 in 25 seconds from now. Now that being said, RIP has built-in mechanisms to try and stop these issues, such as triggered updates. But for now, let's assume that that hasn't been enabled in RIP so that you can see a potential problem. So only 25 seconds from now will router 3 tell router 2 that there's a problem. Router 3 will detect that that interface has gone down and will remove this route from its routing table. So router 3 does not contain network 10.140 any longer. However, router 2, after a period of 15 seconds, assuming that the link went down at 0 seconds, will send an update to router 3 informing router 3 about this network. So router 3 had previously removed the network from its routing table, but router 2 now advertises that network to router 3. So what does router 3 do? Router 3 is going to update its routing table with the new information received from router 2. So it adds the network back to its routing table, but notice the hop count is increased to 2. Previously, before the network went down, this network was in its routing table with a hop count of 0. In other words, it was directly connected on FOSS Ethernet 01. That information was in router 2's routing table. It had learnt about this network from router 3 on interface F01 with a hop count of 1. But now, notice the interface that router 3 learnt about the network on is FOSS Ethernet 00. The hop count has also been incremented to 2. Router 3 believes it can get to this network via router 2, and the network is 2 hops away. Now you may be thinking, well, this shouldn't happen because of split horizon. Now split horizon is one of the mechanisms to stop this behavior. These are the mechanisms to stop loops from taking place. But if these mechanisms hadn't been built into the routing protocol, you would see issues similar to the one I'm demonstrating here. Now because there's a 15-second differential between the updates, 15 seconds later, router 3 sends an update to router 2, informing router 2 about this network. Router 2 then updates its routing table. Notice it believes it can get to the network through FOSS Ethernet 01, with the hop count being set to 3 now, because router 3 informed it about that network with a hop count of 2. So the updates are being advertised between router 2 and router 3. Router 2, 15 seconds later, will advertise that information to router 1. Router 1 updates its routing table, and now the hop count is set to 4. What's the problem? Because of the difference in the clocks, in other words, there's a difference or a differential between the routing updates. Updates between the routers are overriding their routing tables. This will continue, and we'll end up having a loop here where router 2 and router 3 are updating one another every 15 seconds. And if traffic was sent to 10141, this IP address over here, the traffic would bounce between these two routers. They believe that they can get to the network via each other. Notice on router 2 it's pointing to FOSS Ethernet 01, and router 3 believes that it can get to that network via FOSS Ethernet 00, the interface pointing to router 2. So a loop has been formed. The problem is this will continue infinitely. So to combat infinite loops, the developers of the RIP routing protocol have specified that infinity in RIP is 16. So rather than this just continuing on and on and on, a limit is set on the number of hops in RIP to prevent infinite loops. RIP only supports 15 hops between any two networks. This limits the scalability of RIP and limits the size of networks. But RIP isn't designed to run really large networks such as the internet. So one of the mechanisms to stop loops in distance vector routing protocols, including RIP, is counting to infinity. Infinity is set to 16, maximum hop count allowed in RIP is 15. The next one is split horizon. So let's talk about split horizon, route poisoning, and poison reverse. The analogy I like to use for split horizon is that if you told me a really good joke and we have a laugh, I'm not 5 minutes later going to say, I've got a really good joke to tell you, and then I tell you exactly the same joke you've just told me. That doesn't make sense. If you tell me something, I'm not going to tell you what you've just told me. And by the same token, in RIP and other distance vector routing protocols, if router 3 tells router 2 about this network, so notice router 2 has learnt about that network from router 3, router 2 will not send an update about that network on the same interface on which the update was received. So router 2 in pure split horizon does not send the routing update back to router 3. Router 3 is just told it about that network, so it doesn't make sense for it to tell router 3 what it's just been told by router 3. In summary, in RIP, if an update is received on an interface, it's not advertised back out on the same interface on which it was received. It's not useful to send information about a route back in the direction from which the original information came. However, if router 2 learns about this network, 10140, from router 3, it will advertise that information to router 1 because it's sending the update out of a different interface. But because of split horizon, it will not send it back to router 3. By the same token, router 1 will not advertise that information back to router 2. So updates received on one interface will not be advertised back out of that same interface. Now let's go a little bit deeper into split horizon. There are actually two types of split horizon. The first one is simple split horizon, and the second one is split horizon with poisoned reverse. The simple split horizon method is what I've just shown you, and this is where a router learns about an update on an interface and will not send that information back out of the same interface. In other words, when sending updates out of a particular interface, let's say FOST Ethernet 01, we do not include networks learn from updates received on that interface. In other words, router 2 in this example learnt about a route on FOST Ethernet 01. Notice in its routing table, 10140 has been learnt from FOST Ethernet 01. It will not send the update back out of that interface. That is simple split horizon. This is essentially where information is suppressed. Information learnt on one interface is not sent back out of that interface. However, these days, most modern implementations of distance vector routing protocols implement what's called split horizon with poisoned reverse. This includes more information. So rather than not sending that update out of the interface, the router does send the update out, but includes additional information. So when sending updates out of the interface, once again FOST Ethernet 01, the router designates any networks, in this case 10140, learned from updates received on that interface as unreachable. In other words, the metric is set to infinity. This overrides the split horizon rule and is a safer implementation and a more robust implementation of split horizon. So rather than suppressing information, the local router is telling the other router that the network it learned is not available via itself. The local router sets the metric to infinity. In other words, it's informing the other router that the network is unreachable via itself. So router 2, rather than suppressing the update about this network to router 3, is poisoning the route. In other words, setting its value to infinity, and then it's advertising that information using poison reverse, which overrides split horizon, to router 3. So this network is actually advertised to router 3, but router 2 is telling router 3 that that network is inaccessible, essentially telling the router, don't use me to get to that network. Now, poison reverse happens for all networks. So in other words, this network here, 10110, is advertised to router 2 and in turn to router 3. When updates are sent from router 2 to router 1, router 2 includes that network in the update, but it's setting the metric to 16. In other words, router 2 is poisoning the route to router 1. By the same token, router 3 is advertising the same network to router 2, but poisoning it. The disadvantage of poison reverse is that it puts more overhead on the network because routing updates contain more information. They also contain information about routes that have been poisoned. However, it's more robust. So rather than saying nothing, the router uses the premise that bad news is better than no news. With route poisoning, when this link goes down, router 3 is indicating to router 2 that the route is no longer reachable and should be removed from its routing table. So router 2 is told, through what's called a triggered update, which we'll talk about in a moment, that the route is no longer available and should therefore no longer be used. So when this network goes down and is no longer available, router 3 sends the triggered update to router 2, telling it that the metric is 16, in other words, infinity. Router 3 is poisoning the update to router 2. This would prevent a router like router 2 or router 1 sending packets to the invalid route. So thus far, the mechanisms we've discussed are counting to infinity, where infinity is set to 16, split horizon with poison reverse. In other words, the route is poisoned, set to infinity or 16, and that route is advertised back to the originator, overriding split horizon. The last two are triggered updates and hold down timers. These are all mechanisms, once again, to stop loops in distance vector routing protocols. Now, rather than waiting for the periodic or regular update interval, when a network goes down, routers will immediately inform neighbors of that change. So if there's a topology change and there's a change in the routing table, in this case, this network went down and is removed from the local routing table, routers immediately inform neighbors of that change. So router 3 updates router 2 using what's called a triggered update to inform router 2 of the change. Router 2 in turn informs router 1 of the change. So triggered updates, also known as flash updates, are sent immediately rather than waiting for the standard interval, which on RIP is 30 seconds, to send updates when there's a change in the topology. So these triggered updates or flash updates are sent immediately and cascade throughout the network without waiting for the update timer to expire. This allows for quicker convergence rather than relying on the regular scheduled updates. Convergence is a lot quicker because triggered updates are sent immediately upon detection of a topology change rather than waiting for up to 30 seconds to inform neighbors of a change. Whereas triggered updates allow for quicker convergence, hold down timers introduce the concept of not trusting updates for a period of time, which helps reduce the acceptance of bad routing information. Hold down timers can be used to prevent regular update messages from inappropriately reinstating a route that may have gone bad. The hold down timer tells the router to hold any changes that may affect the routes for a period of time. So a router will keep an entry in the routing table marked as possibly down, allowing time for the other routers to recompute this topology change. The route is still available in the routing table so that normal traffic will still be routed to the destination network, as it may have come back during the hold down timer. So if traffic was sent to router 1, it would route the traffic to router 2, even though the route is marked as possibly down during the hold down timer. Router 2 would send the traffic to router 3, and router 3 would either forward the traffic on if the link is up or drop the traffic. Now, in bigger topologies, if router 2 receives an update from a neighboring router with a better metric than the original recorded metric, it will mark the network immediately as accessible and remove the hold down timer. However, if during the hold down timer an update is received from a different neighboring router with the metric being the same, that update from the neighbor is ignored. Ignoring an update with a metric that's the same during the hold down timer allows for more time for the change to propagate throughout the entire network. So we've now discussed counting to infinity, split horizon, route poisoning, poison reverse, hold down timers, and triggered updates. These are mechanisms to stop loops in distance vector routing protocols. Once again, you don't necessarily need to configure all of these because they're built into the routing protocol. In some cases, you might want to disable split horizon. But generally, just by enabling RIP, you get these features. That concludes the second video discussing IP routing. In this video, we looked at the details of how distance vector routing protocols combat routing loops with the use of mechanisms such as split horizon, poison reverse, and others. In the next video, we'll briefly discuss link state routing protocols. For more information, please go to hp.com/go/expert1.